A very good morning, each and everyone. Myself, Professor Satish Hande from the Department of Mathematics, KLS, VDIT, Alia. So, today's topic is example based on the binomial distribution. In the previous topic, we have studied what is binomial distribution and the example based on that binomial distribution. Now, we'll see some more example based on binomial distribution. The probability that a pen manufactured by a factory be defective is 1 by 10. If 12 such pens are manufactured, what is the probability that first one exactly 2 are defective, second at the most 2 are defective, and third none of them are defective? The solution: the probability of defective pen is, that is P is equals to 1 by 10. That is, probability of success is P is equals to 0.1. So that probability of non-defective pen, that is Q is equals to 1 minus P, which is equals to 1 minus 0.1, which is 0.9, and it is already given that n is equals to 12. Here P of x is equals to ncx p raised to x q raised to n minus x. That means it is equals to 12cx 0.1 raised to x into 0.9 raised to 12 minus x. Now, first case, probability that exactly 2 are defective, that is P of x is equals to 2. Wherever x is there, we have to substitute it as 2. So it is 12c2 0.1 raised to 2 0.9 raised to 10, which comes around 0.2301. Now that means probability of that x, the 2 pens are defective, is 0.2301. Then second case, probability that at least 2 are defective, it is probability that x is greater than or equals to 2, which is equals to 1 minus probability of x less than 2, which is equals to 1 minus in the bracket probability that x is equals to 0 plus probability that x is equals to 1. Now that means it is 1 minus in bracket 12c1 0.1 raised to 1 0.9 raised to 12 minus 1 plus 12c0 0.1 raised to 0 into 0.9 raised to 12 minus 0, which comes around 0.3410, and none of them are defective. That means probability that x is equals to 0, which comes around 0.2824. Next example, a lot contains 1% of defective items. What should be the number of items in a random sample so that the probability of finding at least one defective in it is at least 0.75? Let P be the probability of defective item. By the data, P is equals to 1%, that means 0.01. Now Q is equals to 1 minus P, which is 0.99. If x denotes a defective item, then probability of x will be equals to ncx p raised to x q raised to n minus x. So that is equals to ncx into 0.01 raised to x into 0.99 raised to n minus x. Here we need to find n such that probability of finding at least one defective is greater than or equals to 0.75. That means probability that x is greater than or equals to 1 is greater than or equals to 0.75. That means probability of x greater than or equals to 1, which is equals to 1 minus probability of x less than 1, is greater than or equals to 0.75. That means 1 minus probability of x is equals to 0 is greater than or equals to 0.75. So it is 1 minus nc0 0.01 raised to 0 0.99 raised to n minus 0 is greater than or equals to 0.75. That means 1 minus 1 minus 0.99 raised to n is greater than or equals to 0.75. So which is 1 minus 0.75 is greater than or equals to 0.99 raised to n, or 0.25 is greater than or equals to 0.99 raised to n. Taking log on both the sides, log of 25 is greater than or equals to n log 0.99. So it is n is less than or equals to log of 0.25 upon log of 0.99. n is which is less than or equals to minus 1.3862 upon minus 0.0100. This is n is less than or equals to 138.62. That means Taking the equality, n is equals to 138.62. Next example, 4 coins are tossed 100 times and the following results were obtained. Fit a binomial distribution for the data and calculate the theoretical frequencies. Now number of heads are 0, 1, 2, 3, 4 and frequencies are 5, 29, 36, 25 and 5. Here first we need to find mu, which is summation of f of x upon summation of f, which comes around 1.96, and the mean of the binomial distribution mu is equals to np. That means 1.96 is equals to 4 into p. That means p is equals to 1.96 upon 4. This implies p is equals to 0.49. Similarly, q is 1 minus p, which is 0.51. P of x is equals to ncx p raised to x q raised to n minus x. So P of x is 4cx 0.49 raised to x 0.51 raised to 4 minus x. So theoretical frequencies are f of capital F of x is equals to summation of fi into P of xi, which is equals to 100. Summation of fi is 100 upon 4cx into 100 into 4cx into 0.49 raised to x into 0.51 raised to 4 minus x. Now for different values of x, that is f of 0 is 100 into 4c naught 0.49 raised to 0 0.51 raised to 4, which comes around 6.765. f of 1, it will comes as 25.99. f of 2 is 37.47. f of 3 is 24. f of 4 is 57.64. Next example, the number of telephone lines busy at an instant of time is a binomial variate with probability 0.1 that a line is busy. If 10 lines are chosen at random, what is the probability that no line is busy? All lines are busy, at least one line is busy, at the most two lines are busy. Let x denotes the number of telephone lines busy. For this variate, p is given that 0.1, q will be 0.9, n is equals to 10. We have P of x is equals to ncx p raised to x q raised to n minus x, that is 10cx 0.1 raised to x 0.9 raised to 10 minus x. Now first one, probability that no line is busy, that means P of 0, which is 0.9 raised to 10, which is 0.3487 3487. Then second, probability that all lines are busy, that is that it will be 0.1 raised to 10. Next, probability that at least one line is busy, that means 1 minus probability that no line is busy, that means 1 minus probability of 0, it is 0.6513. And the fourth one, probability that at the most two lines are busy, that means it is equals to P of 0 plus P of 1 plus P of 2, which comes around 0.9298. One more example. Now 5 dice were thrown 96 times, and the number of times an odd number actually turned out in the experiment is given. Fit a binomial distribution to this data and calculate the expected frequencies. Now here data given is number of dice showing 1 or 3 or 5, that is 0, 1, 2, 3, 4 and 5. Now corresponding frequency or the observed frequency for no dice showing 1 or 3 or 5, it is 1. 1 dice showing 1 or 3 or 5, it is 10. 2 dice are showing, it is 24. 3 dice are showing 1 or 3 or 5, it is 35. 4 dice showing 18. 5 dice showing, it is 8. Now you can see that here P is the probability of getting 1 or 3 or 5. That means it is equals to, that is 1 minus 1 by 2, which is 1 by 2. This implies P is equals to 3 by 6, which is equals to 1 by 2. So similarly Q is equals to 1 by 2. X denotes the number of times an odd number turning out. Therefore P of x is ncx p raised to x q raised to n minus x. So it is 5cx 1 by 2 raised to x, 1 by 2 raised to 5 minus x. 5cx into 1 by 2 raised to x upon 1 raised to 5 minus x into upon 2 raised to 5 minus x, which comes around 5cx into 1 by 2 raised to 5. Substituting the in expected frequency, that is f of xi will be summation of fi into p of xi. So it is 96 into 5cx into 1 by 2 raised to 5, which is 3 into 5cx. Now f of 0, that is 96 into 5cx into 1 by 3 square, it is 3. Then it is f of 1 will be equals to 15, f of 2 will be equals to 30, f of 3 will be 30, f of 4 will be 15, and f of 5 will be 3. So with this we are completing the example based on the binomial distribution. At the end of the session, students will be able to understand what is binomial distribution and how to solve the example based on binomial distribution. As application, probability distributions are fundamentals concept in statistics. They are used both in theoretical level and practical level. Some practical uses of probability distribution to calculate confidence interval for parameters and to calculate critical region for hypothetical tests. Here are some additional reference given through YouTube channel. I request each and every one of you to go through this YouTube channel. So with this, I conclude today's session. Thank you.